Okay, so that's how you do this in ease. You can also do this using matrix decomposition and Gauss-Seidel iteration. Again, you just have to sort of modify your approach a little bit. So if I want to do this using matrix decomposition, then what I really have to do is linearize my equations, because matrix decomposition only works with linear equations, right? The operation, the linear algebra only works with linear equations. So I can use matrix decomposition to solve linear equations, and the only way I'm going to then converge to the right answer is if I'm changing the coefficients in my linear equation so that I keep getting better and better, which means I'm getting closer and closer to the right answer. Right? So here's the flow chart for what's called successive substitution. And the idea here is you assume a temperature distribution. So a lot like what we just did in ease, we're going to assume some kind of temperature distribution. We'll put a little squiggle over T to indicate that this is just an assumption. Once I've done that, then I can set up A and B, right? Because every place I have to have a conductivity or an electrical resistivity in those coefficients, I can use this assumed temperature distribution to calculate that, right? So this K is being calculated not using these unknown temperatures, but rather using these known, or at least these guessed temperatures, right? Then I can solve the matrix equation just like we did before. That gives me a prediction for the temperatures. It's not the right prediction, right? It's not the right values because it's probably not the same as the temperatures that I assumed to calculate my coefficients. But I can figure out how far apart these two things are. So here's my convergence error. There's all different ways to compute a convergence error. Right? We can take the maximum of the absolute difference between any two nodes, between any node at the previous iteration and the new iteration. Here what I did is I took the RMS value of the difference. Anything that indicates how much it's changed will probably work. Then you look at that error and you compare it to your convergence tolerance. So, in the previous example, I said I want to converge to 1 millikelvin. That's a little bit up to you. You can use some engineering judgment there. If I have converged, then I'm done. If I haven't converged, then I got to do it again, right? And again, one thing I got to remember to do is before I go back around again, I have to set my new value of the guessed temperatures as what I just calculated, right? So I started off with something that I completely assumed. I calculated temperatures, and before I go back again, I'm going to use now the latest set of temperatures as my guessed temperatures. Set up A and B and continue, right? So not too hard, I don't think, right? If you look at the matrix equations, all that's really changed is every place I had a K, now I have a call to a function K, right? But these temperatures, I will know what they are when I'm doing this. So I set up A and B and continue down that path, but within a while loop. So let's see what this looks like in Matlab. So let's see. The first thing to point out here is I set up a function kf, right, which is just my linear variation in k, another function rho, right, and then I can call those functions. So here I have a k and a rho, but these I could get rid of because I'm not going to use them. Instead, I'll call the function every time I need them. Here I am coming down here. I'm going to use sparse matrix allocation again, right? I need a guess set of temperatures, right? So this, if you look in this flowchart, is this right here. I am guessing that the temperatures vary linearly from 300 down to 40. Right, so this is better than I did before. My tolerance is 10 millikelvin. Initially, my error just has to be bigger than my tolerance so that the while loop executes at least once. The while loop is something that will terminate when my error finally gets less than the tolerance. So as long as the error is greater than the tolerance, let's go through and set up A. Right, so this is the same basic equation I had before, except for now I'm calling that function for K, calling the function for K, and calling the function for rho. Same thing down here. I have A and B now, so I can solve for T. The next thing I want to do is see how different the temperatures are here versus the temperatures that I used to set up A and B. So this is my error. And again, I can look at this in the command window. The last thing I'm going to do is set TG equal to T. So if I have to go around again, I'd like to be using my latest set of temperatures, right? And if I run this, you should see a bunch of errors that eventually terminate when I get below 0.01 Kelvin, right? And that answer should be identical to the answer I got from ease to within 0.01 Kelvin, right? Okay, so that's how you do this using matrix decomposition. It got a little bit more complicated because you have to rebuild your A and your B every single time, but I think it's conceptually not that hard to understand. The last thing that we went through was this Gauss-Seidel iteration, right? And actually, that one is really easy to deal with temperature-dependent properties in, because if you think about it, all we had with the Gauss-Seidel iteration was an explicit equation for the temperature at every node in terms of all of the other temperatures, right? So if the other side of that equation gets a little more complicated, who cares? It doesn't really matter, right? So that's what we've done here. We've taken the equations that we have now that involve these function calls for k and rho, and we again just solve for T1. So this is the same equation for T1. It's just that now k is a function of T, and that's fine. And then Ti gives me this equation, and Tn gives me this equation. But the solution technique is exactly the same, right? Here's my explicit equations for the temperatures. What do? I take a set of guess temperatures, right? I use those guess temperatures and go through and recompute every nodal temperature, right? Using always the most recent value of my guess temperatures. And then I see how much it's changed, and if it stopped changing, then I'm done. If it hasn't stopped changing, then I just keep going around and around this loop, right? So in terms of dealing with temperature-dependent properties, Gauss-Seidel is really pretty easy. The only thing I changed in this version of the code versus my original version of the code over here is every place I have a k, now I'm just I'm calculating I'm calling that function, right? And I'm always using the most recent values of temperature to call the function, right? So pretty easy to implement here. If I solve, it should converge pretty quickly, and I get the same solution just one more time using one more different technique. So that's pretty much it for numerical techniques. The takeaways here are, how do you generate the set of equations? And then once you have the set of equations, what are some different techniques you can use to solve them? And how do those techniques change if you end up having some complicating things like temperature-dependent properties and whatnot, which you will, right? Because the whole point of doing the numerical model is you can deal with those kind of complications, right? So this, by the way, this, or I guess if you want to find the ease program, that problem with the temperature-dependent electrical resistivity and thermal conductivity, that's a problem that I could not get an analytical solution for, right? So, if I want to deal with even that simple of a temperature dependence, I'm really kind of stuck going to a numerical solution, and that's pretty trivial actually. So, one last thing to point out is, once I have this running, right, and I have the temperature dependence and everything like that, if I want to check and make sure that this solution is right, how would I do that? What I would probably do is come in here and take these functions and again make them simple, right? So turn them into constant properties, this one and this one, get a solution, and then compare that solution with an analytical solution that I can derive using constant properties, right? So if I can do that kind of comparison between a numerical solution and an analytical solution, then that gives me a lot of faith in the numerical solution, and I can continue down the road of using it to do things like design and optimization and stuff like that.